Welcome. In this video, we'll explore how intelligent agents in AI systems are empowered by two key abilities, using external tools and planning their actions. These capabilities allow agents to go beyond their built-in knowledge, adapt to new situations, and solve real-world problems more effectively. We'll break down what tool use means for agents, the types of tools they can leverage, and how planning algorithms help them sequence actions. By the end, you'll understand how these elements work together to create powerful, adaptable AI systems. Previously, we discussed how agents can reflect on their own processes and learn from experience. This self-awareness enables them to adjust their behavior dynamically. Now, we're taking a step further by combining this with tool use and planning. Imagine an agent not just thinking about its actions, but also choosing the right external resources and planning how to use them. This synergy is what makes modern AI agents so versatile and effective in complex environments. This chapter is structured into four main sections: understanding tool use in agents, exploring planning algorithms, integrating tool use with planning, and reviewing practical implementations. We'll start by defining what tools are in the context of AI agents, then dive into the algorithms that help agents plan their actions. Next, we'll see how these two aspects come together. And finally, we'll look at real-world examples using popular Python frameworks. Let's begin our journey into enabling tool use and planning in agents. To follow along with the practical examples in this chapter, you'll need access to the code files on GitHub and some agentic Python frameworks like CrewAI, AutoGen, and LangChain. These frameworks help demonstrate how agents can use tools and planning algorithms in real applications. Don't worry if you're new to these libraries, our focus will be on the concepts, with code snippets to illustrate key points. At its core, tool use by an intelligent agent means the agent can leverage external resources like APIs, databases, or software functions to enhance its decision-making and capabilities. Instead of being limited to its internal knowledge, the agent can reach out to the world, access real-time data, and perform specialized tasks. This ability transforms agents from isolated problem solvers into dynamic, adaptable systems that can handle a wide range of challenges. Consider an agent asked, "What's the weather?" If it operates in isolation, it can only guess or admit it doesn't know, relying on outdated training data. But if it has access to a real-time weather API, it can provide accurate, up-to-date information. Tool usage lets agents access live data, execute specialized tasks, and manage workflows that go far beyond their built-in knowledge. This distinction is crucial for building agents that can truly interact with the world. The ability to use tools broadens what an agent can achieve. By integrating various tools, agents can offload specific tasks, access supplementary data, and enhance their performance. This means they can tackle complex, real-world challenges that would otherwise be out of reach. Before we dive into the technical details, let's understand how agents actually call tools and functions. In the world of language models, function calling and tool calling are related but distinct. Function calling means the agent generates structured calls to internal functions, like database lookups. Tool calling, on the other hand, lets the agent interact with external APIs or services. For example, retrieving a user profile from a local database is function calling, while querying a weather API is tool calling. Understanding this difference is key to designing agents that can combine internal logic with external resources. When an agent wants to use a tool, it doesn't execute code directly. Instead, it generates a structured response specifying which tool to use, what parameters to pass, and how to format them. Think of the agent as a dispatcher, it writes, detailed instructions, but the actual execution happens in an external environment or by an agent controller. This separation allows agents to focus on decision-making while the system handles execution. Let's look at a typical flow. The agent identifies the need for a tool, generates a structured call, like a JSON object, and passes it to the agent controller. The controller then executes the tool with the given parameters and returns the result to the agent. This modular approach makes it easy to add new tools or update existing ones, and keeps the agent's logic clean and focused. Tools are defined with clear descriptions, either using docstrings in frameworks or JSON schemas when working directly with LLM APIs. Docstrings provide information about what the tool does, required and optional arguments, and expected outputs. This helps the agent understand how and when to use each tool. JSON schemas serve a similar purpose, especially when integrating with models like OpenAI's GPT or Anthropic's Claude. Agents can use a variety of tools, each serving a unique purpose. APIs connect agents to external services for real-time data. Database tools let agents store and retrieve structured information. Utility functions handle specialized tasks like data processing or calculations. Integration tools connect different systems, and hardware interface tools allow agents to interact with physical devices. The right combination of tools enables agents to tackle complex, multifaceted problems. Often, agents need to combine multiple tools to complete a task. This is called tool composition, or chaining. For example, a travel agent might use an API to check flight availability, a database tool to retrieve user preferences, and a utility function to calculate the best itinerary. Chaining tools together allows agents to build sophisticated workflows and deliver more comprehensive solutions. A critical skill for agents is selecting the right tool for the job. Agents evaluate the context, understand the requirements, and choose the most suitable tool or combination of tools. This involves considering tool capabilities, reliability, performance, and cost. Effective tool selection ensures agents can solve problems efficiently and accurately. Agents must be prepared for tool failures, such as API errors or database connection issues. Robust error handling includes detecting failures and switching to alternative tools or strategies when needed. This ensures the agent remains reliable and can continue working even when some tools are unavailable. Many tools maintain state or require specific initialization and cleanup. Agents need to manage these states, handle authentication, and adapt to tool updates or version changes. This includes managing API tokens, database sessions, and ensuring compatibility with new tool versions. Proper state and version management keeps agent workflows smooth and secure. Security is paramount when agents use tools that access sensitive data or critical systems. Agents must manage authentication credentials, enforce authorization checks, and ensure secure communication. Respecting rate limits and usage quotas is also important to prevent abuse or service interruptions. Let's see tool use in action. Imagine a user asks for flight and hotel options for Rome, for 2 adults, with a set budget. Using a framework like CrewAI, the agent is equipped with tools for searching flights and hotels. The agent receives the request, uses the appropriate tools, and returns options that fit the user's criteria. This example highlights tool definition, agent configuration, task specification, tool integration, and execution flow, all working together to deliver a seamless experience. The shift toward tool use is driven by the need to solve complex problems using specialized resources. Instead of building all capabilities into the agent, it's more efficient to leverage the right tools as needed. For example, a healthcare agent might use medical databases and diagnostic algorithms, while a robotic agent could interact with physical machinery. This approach makes agents more scalable, adaptable, and capable of handling diverse challenges. Planning is the process by which agents reason about their actions and devise strategies to achieve their goals. Planning algorithms provide the step-by-step instructions agents use to decide what to do next. In the context of LLM agents, planning must handle natural language, uncertainty, and vast state spaces. Let's explore the main planning algorithms and see which ones are most practical for language-based agents. Classic algorithms like STRIPS, A**, GraphPlan, and Monte Carlo Tree Search, MCTS, have been foundational in AI. However, they're less practical for LLM agents because they rely on rigid state representations and struggle with the ambiguity of natural language. For example, STRIPS works well with binary conditions but can't handle nuanced language states. A-times requires clear cost calculations, which are hard to define for conversations. These limitations make traditional algorithms less suitable for modern, language-driven agents. Fast forward, FF, planning uses heuristic search to guide agents toward their goals. It's moderately practical for LLM agents because it can be adapted to work with natural language, though it requires significant modifications. FF planning's goal-oriented approach aligns with how LLMs handle tasks, but translating numeric heuristics and state representations into language is challenging. Still, with the right adaptations, FF can help agents generate simplified, step-by-step plans. LLM-based planning leverages the natural language understanding of large models to generate flexible, context-aware plans. Instead of explicit state representations, agents use language to describe states and actions. This makes LLM-based planning highly adaptable, able to handle complex, real-world scenarios and ambiguous requirements. Agents can break down goals, generate steps, and adjust plans as new information arises, all using the power of language. Let's see how LLM-based planning works in practice. Imagine a travel planning system with two agents, a strategist who breaks down the request and a researcher who finds options. The strategist analyzes the user's needs and creates a detailed plan. The researcher then validates and fills in the details. This collaborative approach allows agents to handle nuanced requirements, adapt to changes, and deliver comprehensive solutions. While LLM-based planning is powerful, it's not without challenges. Agents can sometimes generate overly optimistic or impractical plans if not properly constrained. They may struggle with strict numerical constraints or timing unless these are explicitly handled. Still, the adaptability and ability to handle uncertainty make LLM-based planning a top choice for many agentic systems. HTN planning breaks down complex tasks into simpler subtasks, creating a hierarchy of actions. This mirrors how humans naturally approach problems, starting with a big goal and dividing it into manageable pieces. HTN is especially practical for LLM agents because it aligns with how language models process and decompose tasks. Agents can work at different levels of abstraction, making planning both structured and flexible. In frameworks like CrewAI, HTN planning is implemented by having a manager agent break down tasks and delegate them to specialists. For example, a travel planner might have separate agents for flights, accommodations, and activities. The manager coordinates these agents, ensuring each subtask is handled by the right expert. This approach is scalable, intuitive, and mirrors real-world workflows. HTN planning offers several benefits. It mirrors human problem-solving, scales well to complex tasks, and allows for reusable patterns across similar problems. Its hierarchical structure makes it easy to encode expert knowledge and adapt to different levels of abstraction. This flexibility is especially valuable in domains like travel planning, healthcare, and robotics. To build truly intelligent agents, we must integrate tool use with planning. Earlier, we saw that planning alone can generate detailed plans, but without tools, the information may be fictional. By combining planning algorithms with real-world tools, agents can ground their responses in facts, access live data, and complete tasks accurately. This integration is the key to building robust, capable agentic systems. Agents need to reason about which tools are available, what each tool can do, and when to use them. This involves understanding tool descriptions, capabilities, and limitations. Modern LLMs are trained to interpret tool documentation and make context-aware decisions about tool selection. However, not all models are equally skilled. Advanced models perform better at tool reasoning, while smaller models may struggle. Even advanced models can face challenges in tool reasoning. They may have difficulty with complex tool combinations, inconsistent selection across scenarios, or struggles with error recovery. That's why frameworks like CrewAI, LangGraph, and AutoGen are often paired with models that have demonstrated strong tool reasoning abilities. Testing and refining agent tool usage is essential before deployment. Modern agents use their language understanding to create flexible, context-aware plans for tool usage. When a request comes in, the agent identifies the goals, determines which tools are needed, and sequences them appropriately. This blends the structure of traditional planning with the adaptability of LLMs, allowing agents to adjust plans as new information becomes available. CrewAI is a Python framework that simplifies tool-based reasoning for agents. Developers can define tools using decorators, assign them to agents, and specify tasks. CrewAI handles the complexity of tool selection and execution, allowing agents to focus on solving the user's problem. This makes it easy to build robust, multi-step workflows for tasks like travel planning. In CrewAI, you might define tools for searching flights, finding hotels, and booking activities. These tools are assigned to an agent with a clear role and goal. When a task is given, CrewAI orchestrates tool usage, processes outputs, and builds a comprehensive response. This approach streamlines development and ensures agents use tools effectively. AutoGen is another platform for building AI agents, focusing on multi-agent collaboration. Agents interact in a round-robin group chat, each contributing to the solution. Specialized agents handle flights, hotels, activities, and summaries, each with their own tools. AutoGen's conversation-based approach enables agents to build on each other's suggestions and create integrated plans. AutoGen uses explicit termination conditions like a summary agent mentioning terminate to end conversations. Tools are associated directly with agents, and the group chat structure ensures all perspectives are considered. This collaborative model is ideal for tasks that benefit from multiple expert viewpoints. LangGraph, part of the LangChain ecosystem, uses a graph-based workflow to manage agent actions and tool usage. The workflow is defined as a state machine, with nodes for agents and tools. The agent node processes messages and decides whether to call a tool or provide a final response. This explicit flow control makes complex workflows easy to visualize and manage. In LangGraph, the workflow cycles between agent and tool nodes. The agent evaluates the current state, decides on tool calls, and the tools node executes them. This cycle continues until a stopping condition is met. LangGraph's approach offers robust state management and clear visualization, though it requires more setup compared to other frameworks. Let's compare CrewAI, AutoGen, and LangGraph. CrewAI offers straightforward implementation with hierarchical or sequential flows. AutoGen excels at multi-agent interaction and conversational workflows. LangGraph provides explicit flow control and robust state management, ideal for complex, graph-based workflows. The right choice depends on your project's needs, workflow complexity, state management, collaboration, and development overhead. In summary, tools and planning are foundational to building intelligent, adaptable AI agents. Tools extend agent capabilities, while planning algorithms help agents sequence actions and achieve goals. Integrating these elements enables agents to solve complex, real-world problems. Frameworks like CrewAI, AutoGen, and LangGraph provide practical ways to implement these concepts, each with unique strengths. Remember, tools are functions that let agents access external services or perform specific tasks. Docstrings and schemas help define tools clearly. Traditional planning algorithms are less practical for LLM agents due to language complexity, while LLM-based and HTN planning offer flexibility and scalability. Reasoning about tools is crucial, but not all models are equally capable. Framework choice should match your workflow needs. In the next video, we'll explore the coordinator, worker, and delegator approach in agentic systems. This model helps agents tackle even more complex, real-world tasks by distributing responsibilities and optimizing workflows. Stay tuned to learn how these roles can further enhance the power and flexibility of AI agents. If you have questions or want to discuss generative AI and LLMs, subscribe our YouTube channel, comment, share, like, and collaborate with us. Engaging with others is a great way to deepen your understanding and stay updated on the latest developments in agentic AI systems. You've now learned how tool use and planning empower AI agents to solve complex problems. By combining external resources with strategic planning, agents become more capable and adaptable. Whether you're building travel planners, healthcare advisors, or robotic systems, these principles will help you create intelligent, effective, agentic solutions. Thanks for watching, and see you in the next video.